Okay, so if you recall from last time, we were talking about the logical positivists and their attempt to develop a logic of scientific discovery. Their ambition was to ground science on as strong a logical foundation as possible. They wanted, in a nutshell, an inductive logic that looked as much like deduction as they could get. Deduction is the kind of logic that guarantees the truth of its conclusions, whereas induction is the kind of logic that makes its conclusions plausible or likely, and they wanted science to be as close to deduction as possible. That was the ambition, at any rate. But it turned out that that project was hopeless. We saw that even though that the logical positivists had made a lot of great contributions and great advancements over the course of the 20th century, their project ultimately ended up proving more or less futile. So if we're going to try to understand how science works, we're going to have to turn away from the positivists and towards something else. So with that in mind, today I want to focus on one of the biggest problems in the philosophy of science, or rather set of problems, that are sort of collectively referred to as problems of induction and problems of confirmation. In other words, we're trying to explain and understand how it is that scientific data relates to scientific theories. More specifically still, how do we know when an observation confirms a scientific theory or supports a scientific theory or lends evidence in favor of a scientific theory? That's something that might seem sort of obvious. It might seem sort of silly. Like, of course, we know when that happens, and we know what the theory says. We know what the theory predicts. We go out and we see if the world actually works the way the theory says it should, and if it does, then the theory is confirmed. But as you can probably imagine at this point, that very little works as neatly or as cleanly as we might expect it to or want it to in science as in philosophy. And these problems are much trickier than you might realize at first glance. So with that in mind, let's start by doing a sort of straightforward example of what looks like a standard example of confirmation. So let's say that I have a theory that says copper conducts electricity. All copper conducts electricity. Well, here's a piece of copper. I could test it and see if it conducts electricity. And if it does, sure enough, I can say, well, this confirms. And by confirms here, I mean it increases the credibility of the hypothesis that all pieces of copper conduct electricity. It doesn't prove it in the sort of logically deductive sense, but certainly the more pieces of copper that you test and the more that conduct electricity, the more confident you can say that your theory that copper conducts electricity is true. So this seems like a pretty standard, straightforward, legitimate example of confirmation. In an ideal world, all examples of confirmation would be this straightforward and this obvious. You have a theory, you test it, the theory is supported, you've confirmed it. But notice the logic of how this works. Notice the logical structure. The logical structure of the theory is all x's are y, and the test, the sample is this x has y, and that seems to sort of confirm it. The logical structure of this example is going to get us into some trouble. If you consider, for example, the following illustration. So this person right here is a third child. I think this is Adam Baldwin. I can't remember which of the Baldwin brothers this is. But whichever one it is, I'm confident he is the third brother of the three. Now, imagine that I had a theory that said all people are third children. Don't ask me where I got such a silly idea from, but if I had such a theory, and then I went out and I tested this theory, and I found Adam Baldwin, or whichever Baldwin this is, I would say, aha, this confirms my theory that all people are third children. Now, this is obviously ridiculous. This is not the way actual science works right here. But what exactly is the difference between this statement and the one about the copper conducting electricity? I hope you can see right away, it's not the logical structure of what's going on here. The logical structure is identical. All x's are y, this x is y, seems to support all x's are y. Whether you're talking about copper conducting electricity or people being third children, both of the logical structures of these two examples are identical. So it can't simply be a question of the logic of the statements in question. That means that if we're going to distinguish examples like this, we want to say the first one is an example of good scientific confirmation, but the second is not. We can't simply look at the logical structure, at the syntactic structure of science. There has to be something about the hypotheses themselves that makes one scientific and the other balderdash. So, in other words, we can't simply understand science by analyzing the logical structure of evidence and theory and seeing how these things relate. We need to actually take a look at the content of these claims. So maybe the difference between these two is that the first one has a law-like structure, and whatever the heck law-like is supposed to mean, that's not entirely clear. That's a bit of another problem for another day, but for now let's sort of assume that we can sort of establish that the first one is supposed to be a law-like structure, whereas the second one is only sort of accidental. It's a coincidence that this person I found happens to be the third person, but it's not a coincidence that this piece of copper conducts electricity. The reason why this piece of copper conducts electricity is because there is a law about the nature of copper and electricity, and these things work in such a way that sort of the fundamental structure of reality itself, the laws of science, entail that one thing must follow. It's not merely an accident in the way this person is a third child seems to work. That's what you'd call an accidental hypothesis as opposed to a law-like hypothesis. Now, this might sound appealing, of course, but if this is what we're going to rest science on, we have to come up with a way of distinguishing law-like hypotheses from accidental hypotheses. And this is actually going to be kind of tricky. This is going to be pretty hard. It's not going to be as simple as saying, well, that's supposed to be law-like and that's supposed to be accidental. We know it when we see it in those two examples, but it's not always going to be that simple. And to illustrate why this is, I want to talk about a fairly old problem in the philosophy of science and the nature of epistemology, which comes from David Hume, who is one of the big-time empiricists, of course, but also was really, really skeptical about the notion of laws of nature. He said that even if there are such things as laws of nature, human beings can never know what they are because we never actually observe laws of nature. What we observe are objects, and we observe things moving. We never observe the laws of nature themselves. So if we're going to be good, honest empiricists, if we're going to say that all knowledge comes from what we see and only what we see, we never actually see laws of nature. We see things behave in certain patterns, and we infer those laws of nature. We say, well, there must be this law here, but the law itself is never actually directly observed. That's always an inference. But for Hume, that's not enough. You cannot say that you have knowledge from that kind of inference. You can only say that you have knowledge from what you observe, and you do not observe laws of nature. And this is what's known as the problem of induction. It's a problem that Hume pioneered 250 some odd years ago, and it has been vexing philosophers ever since. There's been literally hundreds, if not thousands, of papers published on this, trying to resolve this problem, and some of those attempts have been quite admirable and garnered a lot of success, but there really is no sort of set, agreed-upon, universal solution to the problem of induction, even though there are many potential candidates. And Bertrand Russell, I think, illustrated this problem really well with a story of a chicken. So this story is called Russell's Chicken. This is Russell's presentation of the problem of induction, and I'm going to sort of steal it from him because I think it works really well. He says, imagine that we have a chicken on a farm. It's just born, and it's a good empiricist chicken. It's absorbing facts around it. It's from its experiences, and it's learning about the nature of reality that it's being exposed to. And on the first day, the farmer shows up, and right after the farmer shows up, the chicken gets fed. So this is an interesting fact that the chicken notices. It doesn't really understand exactly why it is, but hey, farmer showed up and the chicken got fed. And then the next day, the same thing happens. Farmer shows up, chicken gets fed. Day after that, farmer shows up, chicken gets fed. Farmer shows up, chicken gets fed. You see where this is going. Day in, day out, every single day, the farmer shows up and the chicken gets fed. What kind of conclusion is the chicken going to draw about the relationship between the farmer showing up and the chicken getting fed? Well, if he's a good empiricist and he's going to be sort of allowing himself to make these inferences towards laws of nature, he's going to conclude that there is a law of nature that says every time the farmer shows up, we get fed. Now, if there was a skeptical chicken there, a chicken David Hume, if you will, who said to this chicken, how do you know? How do you know that there's a law of nature that connects us being fed with the farmer showing up? Our first chicken is probably going to say to chicken David Hume, what are you talking about? Don't be ridiculous. All the evidence that we have points to this being a law of nature. Every single day of our lives, the farmer has shown up and we have been fed. All the evidence suggests this is a law of nature. There's absolutely no evidence that contradicts it. What more could you want? Obviously, this is a law of nature. Imagine this chicken's surprise, Bertrand Russell says, when one day the farmer shows up and the chicken gets its head cut off. Damn it. Okay, so obviously the chicken made a mistake. The chicken made some sort of problem. And the question that Russell asks us is, if you could give this chicken advice, general advice, not specific advice. You can't say, hey, don't trust the farmer, he's going to cut your head off. You can't tell him that. But you can give him only sort of general epistemic rules about how you should govern your beliefs. What kind of advice would you give him? And it's really not clear what advice you can give him, because it really does seem like he's relying on good inductive reasoning. He's appealing to evidence. All the evidence supports his theory. None of the evidence contradicts it, but nonetheless, he ends up being wrong anyway. So what is this chicken doing wrong that we're not doing wrong every time we perform a scientific experiment and get the results that seem to support our theories? Or for that matter, even if we're not doing science, even if we're just talking about sort of our common sense folk theories about the way the world works, we seem to draw on this idea that we can confirm these theories through experience. But we're doing the exact same thing that the chicken is in these scenarios. And if the chicken is wrong, then maybe we shouldn't be quite so confident about our own conclusions. So I hope you see the point of this story. It seems to sort of show that the chicken is doing the exact same thing we are. If the chicken's making a mistake, then so are we. And David Hume says, well, if we're going to avoid this mistake, we have to not rely on induction. Now, in point of fact, Hume actually obviously did rely on induction. It's pretty hard to survive without it. But he just said that we shouldn't pretend that we're being rational when we do this. If we're relying on it, we're relying on it out of habit, not because we have good rational justification for thinking this way. So induction may be a powerful force, but like Hume says, the future is under no obligation to mimic the past. Just because things have worked a certain way in the past does not mean that the future must act that way. Hume's famous example here is the idea of the sun rising tomorrow. Do I know right now that the sun will rise tomorrow? Well, I think I know that. That's the kind of thing that sounds like I would say I know that. After all my evidence suggests that that's the way the universe works. Every single day I've been alive, the sun has risen in the morning. But that's exactly the same way that the chicken is reasoning, and the chicken was wrong. So if Hume is right and the future is under no obligation to mimic the past, then we can't really say with deductive confidence that we know that tomorrow all our scientific principles, all our inferences will still hold. It might turn out that all of those turn out to be faulty or false. And that means that we cannot say with confidence that we know any of these things to be true. So the problem of induction undermines a lot of our knowledge, our claims to knowledge, and basically all of science. One way of reading the problem of induction is saying basically that it eviscerates all of science's claims to knowledge.